Welcome to Study Loop.
Okay, we have the formula C2H6O2. And we need to draw all constitutional isomers with this molecular formula that contain an oxygen-oxygen double bond. Now, the one thing that I'll point out is that from our formula of C2H6, we can derive that there are no double bonds and no rings. How do I know this? Because of the double bond equivalency formula, in which you take the number of carbons, which is 2, you subtract the number of hydrogens divided by 2, in this case 6 divided by 2, and then you add 1. And the number you get out, in this case 0, tells you the number of double bonds or rings. Since our double bond equivalence is 0, or it's also called degree of unsaturation, is 0, we know that we have a purely linear molecule. No double bonds, no rings. Okay, so now if we've got 2 carbons and 6 hydrogens to deal with, we know that at some point we're going to have a terminal carbon. For example, if we start with 2 oxygens next to each other, right? Because our options here are to put a carbon on this side or a carbon on this side. And so if I put a carbon on the right-hand side, it has to have a total of 4 bonds, which means I can either then put a hydrogen here, right? At which point I would have to continue outward this way with the other carbon, or I can put a bond to carbon here, at which point I'm out of carbons, and so I'm going to fill in the 4 bonds to this carbon with hydrogens. And at this point, I have 1 hydrogen left, which is good because all of our oxygens should have 2 bonds in the end. So this is one possibility. Let's do that again, but now this time, do our 2 oxygens that are bonded together. We'll put a carbon here, like we did in the first case, but instead of putting a second carbon, we'll put a hydrogen to the right, which then forces us to put another carbon over here and cap it off with hydrogens. Okay, so are there any more isomers? Well, let's start with our 2 oxygens bound together. If I put a carbon on the left-hand side to start with, well, in fact, that's equivalent to, or no different than, putting a carbon on the right-hand side, right? These are equivalent structures. I simply flop one over 180 degrees and it would look exactly the same. So that is not a viable option, meaning at this point my only option would be to put a carbon on the right-hand side. And then what we'll notice is that we've already exhausted all the options for a carbon on the right-hand side. I can either do a carbon with 2 hydrogens and a capping methyl group, CH3, or put a capping methyl group on either side. So at this point, we are done with isomers that contain a peroxy or pair of oxygens bound together. So we can move on to the second half of the question, in which we take the same molecular formula, but consider structures in which the oxygens are not bound together. Now, if the oxygens are not bound together, recall that because hydrogens are always terminal, then our only option is to place a carbon between the oxygens. Right? At least 1 carbon must be between the oxygens. We can't put a hydrogen between the oxygens because we'd be exceeding the octet for hydrogen, right? So this is one way that we can start. Recall that our formula that we're working with is C2H6O2. Okay, from here our options are to either put 2 hydrogens or we could put a carbon here, so that'll be the second one that we'll deal with. Okay, so considering that we put 2 capping hydrogens on either side of this carbon, we know that we have 1 carbon left to deal with, so one of them must go to an oxygen. We're out of carbons. We only have hydrogens left to deal with. So let's just put the remaining 4 hydrogens, 3 of them around the carbon to give it 4 bonds, and 1 of them on this oxygen to give it 2 bonds. So everybody's happy. And as we just stated, we'll redo this example, but once we get to this point where we've got the OCO, rather than putting a hydrogen on either side of this carbon, let's put a hydrogen on one side, and as we stated, a carbon. All right, so this is unique from the other one. At this point, again, we are out of out of carbons, so our only option left is to cap this carbon with hydrogens. We've got 2 hydrogens left, which is perfect because we can assign them to these oxygens and place the remainder of and ensure that the oxygens each have 2 bonds. There is, in fact, 1 structure left. We did oxygen with a single carbon in between, but recall that it is also possible to do oxygen, carbon. Oh, let me scroll down a bit more. Reach the edge of my tablet. We can do oxygen, carbon, carbon, oxygen. And at this point, again, we only have hydrogens left. Each of the oxygens should have 2 bonds total. 2 constituents total. And each of the carbons need a total of 4 bonds. And there we go. At this point, it may be nice to go back and draw bond line representations of each of these molecules. That is, we can see that the more traditional manner of drawing this molecule would be H, O, O, carbon, carbon. And for this molecule, O, O, carbon, carbon. For this molecule, HO, bond to carbon, bond to oxygen, bond to carbon. Hydroxyl, bond to carbon, bond to carbon, bond to hydroxyl. And finally, hydroxyl, bond to carbon, hydroxyl.